Hello everyone, welcome to this session on velocity and acceleration analysis in mechanisms using analytical approach. In the last session, we saw the process to calculate the velocity and acceleration of different points in a mechanism using the complex algebraic approach. In this session, we will take up a numerical problem and we will try to understand further how to calculate the velocity and acceleration of different points in a mechanism. So let me read out the numerical problem first. In a 4-link mechanism, the dimension of the links are as under: AB equal to 50 mm, BC is equal to 66 mm, CD equal to 56 mm, AD equal to 100 mm. AD is the fixed link. Now at an instant when angle DAC, that is the input link, it is making an angle of 60 degree with the positive x direction. The angular velocity of the input link AB is 10.5 radian per second in the counterclockwise direction with an angular retardation of 26 radian per second square. So now what we need to determine: first, angular displacements, angular velocities and angular accelerations of the output link DC and coupler BC. Second, linear velocity and acceleration of point C. So the numerical problem which we have considered here is similar to the one which we took for the graphical approach. Now let us solve this numerical problem using the analytical approach, and in the end we will compare the results obtained with the analytical and graphical techniques. So let us first see what is given to us. So here the length of input link AB is 50 mm. So small a is given as 50 mm. Then the coupler length BC, this is given as 66 mm. So B is equal to 66 mm. Then the output link CD, it is 56 mm. So C is given as 56 mm. And then AD is given as 100 mm. So D is given as 100 mm. Now the angle DAC is given as 60 degrees. So this angle is nothing. This is theta. So theta is equal to 60 degree. The angular velocity of the input link AB, it is given as 10.5 radian per second. So again omega A I am taking as 10.5 radian per second. Now the angular retardation of the input link, that is also given to us. So since it's a angular retardation, so we will consider alpha A as minus 26 radian per second square. Now let us see how can we solve this problem using the analytical technique. So obviously the first step is to solve for these three constants A, B and C, right? So we have already defined the equations for A, B and C, right? So A here it is given as K minus A D minus C cos theta minus C D. So first we will calculate the value of this constant K using this particular equation. So here you can calculate K as A is equal to 50. So 50 square minus B is equal to 66 square, and C is equal to 56. So plus 56 square, then again plus D square. So D is equal to 100. So plus 100 square divided by 2. So this value of K we are getting as 5640. Now this value of K we will substitute here to calculate the value of A. So A is equal to 5640 minus, then this value of A is 50, then D minus C, that means 100 minus 56, then we have cos 60 degree, then again minus C into D. So C is 56 and D is equal to 100. So finally the value of A is equal to minus 1060. Similarly, we can calculate B. So B is equal to minus 2 AC sin theta. So this will become equal to minus 2. Now the value of A is 50, the value of C is 56, and then we have sine of 60 degree. So this will be equal to minus 4850. Then in the end we will calculate the value of C. So C is again K. So K is 5640 minus A. So A is again 50. Then in the bracket we have D plus C. So again D is 100, C is 56. and again we have cos of theta, that is cos of 60 degree, plus CD, so plus C is again 56, D is 100, so plus 56 multiplied by 100, so this will give you 7340. Now once we have calculated the values of A, B and C, we will directly apply the formula phi equal to 2 tan inverse minus B square root of B square minus 4AC divided by 2A. Now this will give you 2 tan inverse 1.199 or minus 5.759. So here you can observe you can have two values of phi. So we are going to pick up this first value, that is phi is equal to 100.35 degree for further analysis. Now let's see in the same way, in the same manner, right, you can calculate for beta. So again for beta the equations are already defined, right, we have already seen these equations in the previous session. So now we can substitute the values of k prime and then A, B, C and theta, right, to get the values of E, D and F, and finally we can calculate this beta, right. So beta is coming equal to 10.29 degree. Now after calculation of phi and beta, now we will go for the calculation of angular velocities. So again angular velocity formula we know, this is equal to, so we are going to initially calculate the angular velocity of output link CD, that is omega C. So omega C is equal to A omega A sine beta minus theta divided by C sine beta minus phi. So here we have A 50 multiplied by omega A 10.5 multiplied by sine in the bracket, then we have beta minus theta. So this is 10.29 minus 60 degree divided by, then again we have C, so C is 56 and again we have sine, then beta minus phi, that is 10.29 minus 100.35. So now you can see here, so once you have obtained the value of phi and beta from the displacement analysis or position analysis, you can directly substitute these values, right, to calculate for omega C. So again I am mentioning here, before going for velocity analysis, you always need to perform the position analysis first. Now let us see how can we calculate omega B. So again omega C is coming equal to 7.15 radian per second. Now omega B is equal to minus A omega A sine phi minus theta divided by B sine phi minus beta. Now we will again substitute these values here. So let me quickly show you. So again this will be minus 50 multiplied by 10.5 multiplied by sine, then 100.35 minus 60 divided by 66 multiplied by sine, 100 minus 35 minus 10.29. So from here you can calculate omega B as minus 5.15 radian per second. Now after the calculation of angular velocities, we will move to the calculation of angular accelerations. Now let us see how can we calculate the angular accelerations. So again the equation for angular acceleration of output link CD, this is given as alpha C equal to A alpha A sine beta minus theta minus A omega A square cos beta minus theta minus B omega B square plus C omega C square cos beta minus phi divided by C sine beta minus phi. Now let us calculate alpha C. So alpha C is equal to 50, right, that is A multiplied by alpha A. So alpha A is minus 26 multiplied by sine of beta minus theta. So beta is 10.29 minus theta, theta is 60 degree. Then we have minus 50. So again A omega is A square. So this is A equal to 50 and omega A square we already know, omega A is 10.5. Then multiplied by cos of beta minus theta. So again cos of 10.29 minus 60 degree, right, minus 66 multiplied by, right, 5.15 square, that is this, minus B omega B square. Then we have plus C omega C square. So this is C. So little bit of correction here. So this is C 56 then multiplied by omega C square, that is 7.15 square, then multiplied by cos of 10.29 degree minus 100.35 degree. So again this is cos of beta minus phi. So this is your beta and this is your phi. Divided by again c sin beta minus phi. So c is 56, then sin, and beta is 10.29 minus phi is 100.35. So from here we can calculate the acceleration value as 76.26 radian per second square. Now similarly we can calculate the angular velocity of link BC, that is alpha b. So let us see how can we calculate alpha b. So alpha b is nothing, this is equal to a 50 multiplied by alpha a, that is minus 26. Then we have sine of phi minus theta. So sine of 100.35 minus 60 degree. Then we have minus a omega a square cos of phi minus theta. So a omega a square is 50 multiplied by 10.5 square multiplied by cos of 100.35 minus 60 degree. Then we have minus b omega b square. So minus b is 66, omega b is 5.15 square. Then we have cos of phi minus beta. So cos of phi is 100.35, then minus beta is 10.29, plus we have 56 c omega c square, that is c is 56, then omega c square is 7.15 square, divided by, then we have 56 b sin beta minus phi. So b is equal to 56, then we have sine of 10.29 minus 100.35. So finally alpha b we can calculate from here. So okay, so let's correct it here. So this is 66 actually. So the length of this is given as b is equal to 66. So here we can calculate and we can substitute those values. So finally we can get alpha b as 32.98 radian per second square. Now if you observe carefully, right, the difference between these two equations is, see, most of the coefficients for this sine and cos terms, they are almost same. So here you will find only difference is that here actually in place of, right, here in place of beta, right, if you move to alpha b you have phi, correct, and then again in the third term if you observe carefully, right, this cos beta minus phi, right, it will come on this side, and then this c omega c square, it won't have any cos term associated with it, right. So if you just try to observe the difference between these two formulas, right, so somewhere just try to create a similarity between these two equations so that you can remember it for let's say solving numerical problems. Now after this let us move to calculation of linear velocity of point C. So as I have mentioned earlier, once you have calculated the angular velocities and angular accelerations of all the links in the mechanism, it becomes very easy to calculate their linear velocities and linear accelerations. So let us see, let's say we are interested into calculating the linear velocity of point C. So we can simply calculate this by invoking this relation, that is v equal to r omega, where this r is nothing, this is distance of the point from the center of rotation. So here we know that linear velocity of point C, Vc, is equal to simply Cd multiplied by omega c, where you can see that this Cd is nothing, this is this distance r, right, of point C from center of rotation d, right. So here we can easily substitute this value, that is 0.056 multiplied by 7.15, this will give you 0.04 meter per second. Now here again let us see how can we calculate the linear acceleration of point C. So again for calculating the linear acceleration of point C, we know that this will have two components. One is the centripetal component. So centripetal component FCDC, this will simply become equal to CD multiplied by omega c square. So this will be 0.056 multiplied by 7.15 square. So this will give you 2.86 meter per second square. And then we have the tangential component, that is FCDT, which is simply given by R alpha, or you can simply say CD into alpha c. So this will be equal to 0.056 multiplied by 77.26, and this is going to give you 4.33 meter per second square. Now this is the centripetal and tangential acceleration component, the total acceleration component, it will simply become equal to square root of the centripetal component square plus the tangential component square. So this will be equal to square root of 2.86 square plus 4.33 square, and finally you will have the linear acceleration of point C as 5.19 meter per second square. Now if you remember, right, we took the same numerical problem, right, and solved it using the graphical approach. While solving it through the graphical approach, we observed the acceleration value close to 6.15 meter per second square. So if you simply subtract these two values, right, from the graphical and analytical approach, you will simply get an error of approximately 0.96 meter per second square. So that is the reason while drawing, right, the vectors in the graphical approach, we have to be very careful while moving the scales from one location to another, and then again like checking or calculating the magnitudes of the individual vectors in the acceleration or velocity vector diagram. Now with this, I would like to conclude this session, and this is the end of the second module of the Kinematics of Machines course. So I hope you liked this module and you learned a lot from this module. So please leave your feedback for this particular course and let me know if you have specific doubts in any of the concepts. I will be happy to solve it for you. Thank you.